So the work we've done so far has been pretty abstract. So let's make it concrete with a situation that we're all pretty familiar with, which is I have a wire. That wire has a steady current that runs down it. The wire has some thickness, so it has a radius A, and the current is being transported along the z hat direction. So we know that there is an electric field that's going to be associated with that current, right? We have to drive it, and it is a constant electric field. So as a result, we have a current density that is uniform, namely equal to sigma E0 times z hat. We also know that we can calculate the magnetic field inside of the wire using Ampere's law. We're not going to go through that because we've done it a lot of times. So it's mu naught j pi r squared, which is the area, divided by 2 pi r, which would be the circumference. And we know that it points in the phi hat direction. That is, it sort of goes around the current. Now this, very simply, with our relationships that we have for the current density, gives us something that changes linearly with the distance away from the center. We've also seen that a number of times before. Now, if we want to calculate what is going on with the Poynting vector, right, we have to pick a location to do that. We could find it in general, but what we want to do is actually find it on the edge of the wire, so right around here. And the reason for that is because we're going to look at how that energy gets transported across the boundary. So that is equal to E cross B divided by mu 0. And if we go ahead and calculate that, we're going to have the conductivity times the magnitude of the electric field squared divided by 2. The R is actually equal to A. And then we will cross z hat and phi hat. This is really important right here because it tells us the direction, which happens to be in the minus s hat direction, that is radially inward. So when you're looking at the flow of energy across this boundary, it points in, which is important because that's actually what is changing the mechanical energy of the charges. It's the thing, so there's a cross section here. It's the energy transport across that boundary that is driving the charges to move around. Now, we'll do a couple of quick things to make sense of that. So if we considered some length of the wire, so let's just say we cut the wire here and we're looking at this length of it. Across this length, the potential difference is going to be equal to E0 times the length, right? That's just how much the potential difference across that changes for a steady or a constant electric field. The total current, on the other hand, is equal to the current density times pi a squared, and in this case, that's sigma epsilon E0 pi a squared. That's the total amount of current that is carried across the boundary if we were to integrate across that area. So what we can do is we can look at our statement of energy conservation, namely that the time derivative of the work that's done on charges times the plus the change in the electromagnetic energy is related to the total outflow of energy by the Poynting vector. In this case, E and B do not change with time. And so the electromagnetic energy change is 0. It doesn't contribute. So it's not that it itself is 0, but that the time rate of change of it is 0. And so let's make that more explicit. That is that the time derivative of that is 0. And so what we actually care about is how much work we're doing on charges. That turns out to be related to this integral of the energy transport over this cylindrical surface that we have here associated with the wire. So right, this guy right here. So that is very simply the Poynting vector that we calculated earlier at the boundary, which is sigma epsilon E0 squared divided by 2 times A, and it points in the minus s hat direction. And to that, we are going to dot the area of the region that we're interested in, which is simply 2 pi a, that's the circumference, times the length, and that points in the s hat direction. The reason for that is that dA in this case points outward. And so taking that all together, the time rate of change of the mechanical energy associated with the charges is going to be plus sigma uh, E0 times pi a squared times E0 L. That just cleans up. So what we did was sort of group terms in a thoughtful way. This right here is the current. This right here is the potential difference across that region. And this is the power. It's what's the rate of change of the mechanical energy associated with charges. So what we have derived here is what we've always talked about, which is that the power dissipated in some region of space is just the current times the voltage.